Welcome. Today we will discuss iron and cobalt based reagents. So, you can see in the periodic table iron and cobalt, they are neighboring elements and they are in the same row, and iron is D6 system and cobalt is D7 system. So, first we will discuss iron based reagents in organic synthesis. We will discuss Coleman's reagent, which is Na2 iron tetracarbonyl, then binary carbonyl iron complexes, alkene iron complexes, cyclopentadienyl iron carbonyl also will discuss, Friedel-Crafts alkylation will discuss, epoxidation will discuss, Kharas reaction will discuss, that is the difunctionalization of alkenes, aminochlorination we will discuss, allylic oxidation, that is the allylic alcohol formation we will discuss, and cross coupling reaction, Kumada, Negesi, Suzuki kind of reactions we will discuss. So, organoiron chemistry is the chemistry of iron compounds containing a carbon to iron chemical bond. Organoiron compounds are relevant in organic synthesis as reagents such as iron pentacarbonyl, diiron nonacarbonyl and disodium tetracarbonyl ferrate. Organoiron chemistry was started by the discovery of pentacarbonyl iron in 1891. So, 1891 first iron pentacarbonyl was discovered independently by Mond and Bartlett. In complexes, iron has an electronic configuration argon 4s0 3d8. The most common oxidation state for iron are +2 and +3, and iron 2 complexes argon 4s0 3d6 having a coordination number of 6 with an octahedral ligands pair is preferred, and iron 3, that is 4s0 3d5 can coordinate 3 to 8 ligands and often exhibits an octahedral coordination. So, here also octahedral coordination is observed. Iron 3 generally is a harder Lewis acid than iron 2 and thus binds to hard Lewis bases. Iron 0 mostly coordinates 5 or 6 ligands with trigonal, bipyramidal and octahedral geometry. So, first we will discuss Coleman's reagent Na2FeCO4. So, reaction of the nucleophilic Coleman's reagent with two alkyl halides affords ketones via successive oxidative addition. So, alkyl halide goes to ketone, that we will see, and of course, the carbonyl group comes from the carbon monoxide. The reductive elimination eventually releases the newly formed organic product in a concerted mechanism. So, this is the reaction Coleman's reagent. Now, Rx comes, oxidative addition happens and you get this pentacoordinated iron, one R is here and sodium plus is outside. Now, the insertion will happen. So, one carbon monoxide inserts into this iron R bond. So, this is formed carbonyl, and now a ligand can be solvent or carbon monoxide again reacts with iron. So, that iron becomes pentacoordinate now, and oxidative addition again will happen with another alkyl halide R-X. So, R-X adds here and iron now is hexacoordinate. So, iron becomes hexacoordinate. So, obvious is that now the reductive elimination will happen. So, reductive elimination, so R dash they are close to this COR group. So, that is they are C. So, this reductive elimination can be possible now and you get the ketone, and also with another ligand comes, then you get this FeCO3L2. So, this is the byproduct. So, what happens? One alkyl halide and another alkyl halide reacts with Coleman's reagent, and in this process you can get a carbonyl. So, the carbonyl group is coming from carbon monoxide. form carbon monoxide. This was reviewed in iron compounds in organic synthesis, Academic Press, London, 1994. So, now we will discuss binary carbonyl iron complexes. Iron forms 3 stable homoleptic complexes with carbon monoxide. Pentacarbonyl iron FeCO5, nonacarbonyl diiron Fe2CO9 and duodecacarbonyl triiron Fe3CO12. So, iron can be only one iron, that is iron pentacarbonyl, 2 iron can be there, that is Fe2CO9, and 3 iron is there, Fe3CO12. So, these are the structure iron pentacarbonyl. You can see 5 carbon monoxides are there around iron, and this is structure of Fe2CO9. Here you can see 3 carbon monoxides are here, 3 are here, and remaining 3 are in the bridged. So, they are bridged. And also there is a iron-iron bond here that can be seen. Similarly, Fe3CO12, here 2 iron has 3 carbon monoxide and 1 iron has 4 carbon monoxide. So, 4 plus 3 is equal to 10, and remaining 2 carbon monoxide are in the bridged. So, they are bridged, and also there is a iron-iron bond. So, it is important in Fe3CO12, 2 iron will have 3 carbon monoxide and 1 iron will have 4 carbon monoxide, and 2 carbon monoxide are in the bridged. So, bridged carbon monoxide are labile, of course, and this was reviewed in Account Chemical Research 1979. So, we will discuss more about binary carbonyl iron complexes and reaction also. The reaction of 2 alkynes in the presence of pentacarbonyl iron affords tricarbonyl eta 4 cyclopentadienone complexes via a 2 plus 2 plus 1 cycloaddition. An initial ligand exchange of 2 carbon monoxide ligands by 2 alkynes generating a tricarbonyl bis eta 2 alkyne iron complex followed by an oxidative cyclization generates an intermediate ferrocyclopentadiene. So, this is the reaction. If you see, this is the iron pentacarbonyl 18 electron, and after heating 1 carbon monoxide eliminates, you get this 16 electron tetracarbonyl iron, and now the ligand exchange will happen. So, triple bond, that is the alkyne can add to the iron and you get another 18 electron, and now again another carbon monoxide after heating can eliminate. So, it becomes again 16 electron, and again another alkyne will come. So, you get this 18 electron species. Now, this oxidative coupling will happen. So, oxidate generates an intermediate ferrocyclopentadiene. So, this forms, this is the oxidative coupling happens, and you get this ferrocyclopentadiene. So, this is the, you can see cyclopentadiene with iron. So, that is called ferrocyclopentadiene, and 3 carbon monoxide are there, and this can after reductive elimination gives this cyclobutadiene FeCO3 complex, that is potential byproduct, and major thing happens that again another carbon monoxide comes and you get this 18 electron, and now the insertion will happen. So, insertion of carbon monoxide and subsequent reductive elimination lead to the tricarbonyl eta 4 cyclopentadienone iron complex. So, after insertion, so here you see carbon monoxide inserts into this carbon iron bond and you get this 6-member ring, which is of course 16 electron system, the iron, and after reductive elimination you get this. This is the product 18 electron compound, that is the tricarbonyl eta 4 cyclopentadienone iron complex. So, this is the product after reductive elimination 18 electron, and also this is a byproduct, that is the cyclobutadiene tricarbonyl iron, that is the byproduct, and this is the major product cyclopentadienone. These cyclopentadienone iron complexes are fairly stable, but can be demethylated to their corresponding free ligands. So, here also you can demetallate, that iron can be removed and you can get free cyclopentadienone. This was published in Justus Liebig's and Chemist 1953. Now we will discuss alkene iron complexes. Neutral eta 2 alkene tetracarbonyl iron complexes can be prepared from the corresponding alkene and non-carbonyl diiron via a dissociative mechanism. The organic ligand in the alkene iron complex is more easily attacked by nucleophiles than the corresponding free alkene due to the acceptor character of the tetracarbonyl iron fragment. So, this is important. When a olefin is connected to iron tetracarbonyl, this becomes an electrophilic species. So, electrophilic species, and now a nucleophile can come and you get this complex. So, you can see the nucleophile added and this FeCO4 now connected to one carbon and overall a negative charge is there, and now this can react with H plus. So, if you react with H plus, then this iron tetracarbonyl can be removed and you can get formal addition of nucleophile to olefin. So, an alkane is formed here. So, this is alkane with the nucleophile. Also, if you put Rx, this is interesting, if you put Rx, then a COR group will come. So, one carbon monoxide inserts into the carbon iron bond and then R adds. So, you get this compound. So, one side nucleophile, another side COR group, and this was published in Chemcom 1977. On the other hand, cationic alkene complex. So, this is anionic. Now, cationic alkene complex of the type eta 2 alkene F plus, F is equal to Cp FeCO2 are available by reaction of the alkenes with Cp FeCO2 Br. The Fp fragment serves as protecting group for alkenes and tolerates bromination and hydrogenation of other double bonds present in the molecule. Due to their positive charge, eta 2 alkene Fe plus complexes react with a wide range of nucleophiles such as enamines, enolates, silyl enol ethers, phosphine, thiols and amines. So, alkene iron complexes, the addition proceeds stereoselectively with the nucleophile approaching anti to the Fe group, but often shows poor regioselectivity. And this drawback is overcome by using vinyl ether complexes which are attacked by nucleophiles exclusively at the alkoxy substituted carbon. So, this is important. If you use vinyl ether, then the nucleophiles adds exclusively at the alkoxy substituted carbon, and this intermediate alkyl Fe complex undergo elimination of alcohol and demetallation. So, this is the reaction Fp. So, Fp connected this is electrophile and this is the enolate derived from cyclohexanone lithium aluminate. Now, if you do the reaction THF minus 78 degree centigrade, you get this carbon carbon bond formation and OET comes here. The attack is happening alkoxy substituted carbon. And now, this ether as well as Fp can be removed in two-step process. First treatment with HbF4 ether dichloromethane minus 78 degree centigrade followed by NaI acetone, you get this. And this is a very interesting product. This is actually vinylation of enolate. So, this is alpha vinyl ketone which can be obtained. So, this alpha vinyl ketone are important compounds and difficult to obtain, but in this strategy you can get this alpha vinyl ketone. This was published in Pure Applied Chemistry 1984. Now, we will discuss cyclopentadienyl iron carbonyl. So, reaction of Fe2CO5, this is Fe2CO5 with cyclopentadiene gives the dimeric iron dicarbonyl complex. So, this is the cyclopentadiene iron dicarbonyl complex. This can be obtained after heating with cyclopentadiene at 200 degree centigrade, and this is the structure of cyclopentadiene iron dicarbonyl. So, this you can see this is dimeric and there is a bridging CO. So, one CO is connected to iron each and another two are in the bridge. Also this is a debate that there might be a iron-iron bond also. And now if you put base, then this can be converted to anionic CpFeCO2m. So, suppose this is the iron cyclopentadiene dicarbonyl, if you treat with sodium hydroxide, then you get this anion. This can be obtained in the presence of base like sodium hydroxide, and the latter can be reacted with an array of acid chlorides, alkyl halides and acids to give the corresponding organoiron derivatives. So, different reactions can be performed on this, and if you see this structure, there is a negative charge on the iron and sodium of course is plus. Now, if you treat with H plus, then you get this CpFeCO2H. Alternatively, if you react with RCOCl, then this iron is reacting. So, iron is reacting with RCOCl and you get this FeCOR with the elimination of minus sodium chloride. On the other hand, if you react with Rx, then the iron takes the R and again you get sodium chloride elimination. So, this is very important. If you put with sodium hydroxide, then you can get this CpFeCO2m like sodium, and then you can treat either acid or acid chloride or alkyl halide to get defined organoiron compounds. Now, we will see different reactions of iron. Iron is generally a Lewis acid catalyst. So, we will see first the Friedel-Crafts alkylation. Friedel-Crafts alkylation involves the alkylation of an aromatic ring with an alkyl halide using a strong Lewis acid such as aluminum chloride, ferric chloride or other MXN reagent as catalyst. The general mechanism for tertiary alkyl halides is shown below. So, like this benzene Rx. So, this can be tertiary also, tertiary alkyl halide, because there the carbocation will form much easier. And now ferric chloride is the catalyst with minus HX, you get this. So, this benzene becomes substituted benzene. Or this is called alkylation, alkylation of benzene. So, what could be the mechanism? So, FBr3 is Lewis acid, so it can react with X and there will be delta plus charge on the carbon connecting to R, and that is the stabilized. So, here you get this carbocation after addition, and FeBr3X minus is the byproduct. Now, this carbocation is stable actually. So, this is stable by delocalization, because these pi bonds will help in the delocalization of this. So, this is quite stable and the different resonating structure can be drawn for this. And after that FeBr3X minus can take up this proton and the aromatization will happen and you get this product plus FeBr3 and HX. So, FeBr3 HX are the byproducts and this is actually the catalyst. So, HX is the byproduct. Catalyst is regenerated. For example, this one, if you see this substrate, there is a olefin is here and there is a ketone is here, but if you see this benzene has the substituent here, now this ortho position is here or here, but both are same. Now, this one if it attacks here and the carbocation which is stable, that will form. So, this is the tertiary carbocation like, so this will be stable. So, this carbon attacks here. So, Friedel-Crafts reaction will happens to here and you get this compound. So, this is very important. The carbonyl group is undisturbed in this reaction. So, only 0.1 equivalent ferric chloride dichloroethane solvent, room temperature 1 to 71 hours, you get this product. This was published in Organic Letters 2018. Now, we will discuss epoxidation. So, Jacobson group reported an iron catalyzed epoxidation in 2001. So, this is one decan when treated with hydrogen peroxide 1.5 equivalent, ligand iron 2 MECN2 SbF6 to 3 mole %. So, this is the ligand. If you see, this is C2 symmetric ligand, and here this is tertiary amine and also pyridine motifs. This binds with iron, of course, and iron reacts with H2O2 to generate this iron oxo bond is formed, and that is why the epoxidation is happening. Also, acetic acid is required 30 mole %, acetonitrile solvent 4 degree centigrade temperature. In 5 minutes you get this epoxidation. So, this is a very fast process, very fast. You get this epoxide in 85% yield. This was published in JACS 2001. Now, Baylor also reported the epoxidation reaction. Suppose this is trans-stilbene. So, trans-stilbene when reacted with hydrogen peroxide 2 equivalent FeCl3 6H2O 5 mole %, H2-PDIC. This is actually pyridine dicarboxylic acid. This is called H2-PDIC short form, and ligand 12 mole %. So, this is the structure of ligand. Here you can see a sulforamide group is there and a secondary amine is there, and this is the solvent 2-methyl butanol. Room temperature you get this epoxide 98% yield. However, the enantiomeric excess is low, only 36% enantiomeric excess is obtained. So, with this chiral ligand they got 36% enantiomeric excess, and this was published in Angmo and the Chemi International Edition 2007. Now, we will discuss Khara's reaction. So, Khara's first described the addition of halocarbons to alkenes in 1945. So, this is the reaction, the alkene CXCl3 with iron. Here the difunctionalization happens and you get this RCCl here and XCl2 here, X is equal to hydrogen chlorine bromine. So, this was published in Science 1945. Now, Mori and Suji reported the formation of lactone ester when methyl trichloroacetate was used. Here you see with this one methyl trichloroacetate. So, methyl trichloroacetate, you get this product. So, here this center this group is coming and 2 chlorine CCl2 groups adding here this carbon. Earlier we have seen here this Cl coming and this group CXCl2 is coming here, terminal carbon. So, here this product you can get in 46% yield after treating with cyclopentadiene FeCO2 that structure we have seen earlier 0.8 mole % and 150 degree centigrade temperature 16 hours, you get this product 46% yield. Along with this product here chlorine comes, this group comes at the terminal carbon and you get this product in 13% yield. This was published in Tetrahedron 1972. Now, Suji also reported the addition of carbon tetrachloride to generate Khara's products as well as acyl chloride. So, this you can see this is 1-octene. 1-octene when treated with carbon tetrachloride, same compound CpFeCO2 dimeric 4.5 mole % only. Also, carbon monoxide you have to add 200 atmosphere. This is the reaction is another in 118 degree centigrade 15 hours you get this product. So, this is of course coming from the carbon monoxide and that is the COCl group is coming here and the terminal carbon there is CCl3. So, earlier also the terminal carbon we have seen CCl3 is adding and this product is forming 41% and this product here the chlorine is adding and CCl3 terminal carbon. This is product is obtaining 21% yield, and this was published in Journal of Organic Chemistry 1970. So, now we will see a different reaction, aminochlorination. So, this is also difunctionalization of olefins. Bach reported intramolecular aminochlorination, and with this acyl azide, and there of course is olefin is there. Now, with ferrous chloride 10 mole percent, TMS chloride 1.5 equivalent ethanol 0 degree centigrade to room temperature, in 21 hours you get this product. So, cyclic carbamate is formed, carbamate, and there is a two stereocenter you can see. So, the major is forming trans in 91:9 ratio, and the most likely the mechanism follows radical intermediates. So, first radical A will form, if you see from this azide and ferrous chloride you get this. So, there is a radical on nitrogen which is connected to iron. Now, this radical of course will add to this double bond, because a 5-member ring will form, and after the 5-member ring formation you get this radical B, and with a radical at this carbon which is connected to R, and this was published in Synthesis 2006. This radical of course will react with the solvent and can be quenched, so that formal, or it can react with Cl group, or it can react with Cl to get a Cl group here. Leads aminochlorination of cyclopropene. So, this is cyclopropene, and this is NN dichlorosulfonamide, with ferric chloride 20 mole percent acetonitrile you get this. So, what happens, the chlorine adds here, of course chlorine is nucleophile, and NH tosyl is here the most substituted carbon atom. So, this is the difunctionalization of olefin. So, what could be the mechanism? So, with ferric chloride catalytic amount, because 20 mole percent is added, and with this reagent you get this. So, aziridinium cation is forming. Here the nitrogen has a positive charge. So, tosyl NCl2 in presence of acid first makes the aziridinium ion. Now, the Cl minus will attack here. So, you get this Cl here, and this group is open also with Cl minus elimination you get this product. So, one side chlorine and another side NH tosyl groups adds. This was published in Organic Letters 2006. Now, we will see different cross coupling reactions. So, we have earlier seen the palladium and copper purpose many cross coupling reaction. Here we will see iron can also perform, because iron is very cheap. First report of iron mediated cross coupling came from Kharas and Fields in 1941. So, phenyl magnesium bromide with bromobenzene, only 5 mole percent ferric chloride ether will give this biphenyl. Biphenyl will be formed in 47% yield. This was published in Journal of American Chemical Society in 1941. Kochi reported the coupling of alkynyl halides with Gigner reagents in 1971. So, exactly after 30 years, Kochi developed the reaction again with alkynyl bromide. So, RMGR alkynyl bromide 5 mole percent ferric chloride THF, you get this alkene. So, here alkene is formed, which are much useful alkene synthesis, and you see here trans alkene, trans 2-butene, cis 2-butene is formed in very high yield. Here a long chain can be formed in 83% yield. Here also 2 olefins are there. This selectively forms in 64% yield. and trans reacts 15 times faster than cis. So, if you have a trans one, that will react 15 times faster than cis, of course, for the steric region, and the olefin geometry will be retained. So, coupling of alkynyl halides occurs stereospecifically. So, the geometry will remain intact. So, trans will give trans olefin, cis will give cis olefin. This was published in Journal of American Chemical Society 1971. Now, we will discuss the mechanism. So, Cauchy proposed an iron 1, iron 3 mechanistic cycle. So, if you see the cycle, iron 1 is the active catalyst here, and with this alkynyl bromide oxidative addition happens like palladium. Here this iron will be 3 now after oxidative addition, and now this MgBr will come, and so this is called the transmetallation TM. So, MgBr, the R group will coordinate with iron, and MgBr will react with this Br. So, MgBr2 will form, and here also iron is 3, and now reductive elimination will happen. So, after reductive elimination you get this olefin product, olefin is formed, and your iron 3 becomes now iron 1 after reductive elimination. So, the mechanism is similar like palladium catalysis. Here iron 1 is the active catalyst, and in the reaction it becomes iron 3 also, and after catalytic cycle again it is coming back to iron 1. Now, we will discuss Negishi coupling. Nakamura extended iron catalyzed cross coupling to organozincs for milder protocol. Here diphenyl zinc with cycloheptanyl bromide with 5 mole percent ferric chloride TMEDA 1.5 equivalent THA 50 degree centigrade 30 minutes, you get this cross coupled product in 96% yield. Organozinc is prepared in situ from aryl gingnite and zinc chloride, that also we have seen earlier, and use of TMS-CH2 non-transferable ligand improves substrate economy, like here instead of another phenyl group, if you put the CH2 TMS which is much smaller in size with the same bromides, cycloheptyl bromide 5 mole percent ferric chloride TMEDA 1.5 equivalent THA 50 degree centigrade, you get this product again 95% yield. This was published in Sinlet 2005. And cross coupling occurs with retention of olefin stereochemistry, like earlier also you have seen for Kumada coupling. Here also Negishi coupling, this suppose is Z configuration, this is alkyl bromide also functionalized, 5 mole percent ferric chloride TMEDA 5 equivalent THF 30 degree centigrade, you get this olefin, and here also this is Z. So, the stereochemistry is retained, and R is equal to here CH2SiMe3 like here, and 96% Z and 87% yield. CO2 ET group is untouched in this reaction. Now, Suzuki-Moira coupling, first iron catalyst Suzuki-Moira coupling was reported by Young in 2008. This is the aryl bromide, aryl boronic acid with 5 mole percent ferric chloride, 10 mole percent DPPY, diphenyl pyridine, KFKOH, 15 kilobar 100 degree centigrade THF, you get this cross coupled product in 67% yield. High pressure is presumably assisting reduction of FeCl3 down to low valent active state, iron 1 state. That is why high pressure is required. This was published in Tetrahedron Letter 2008. However, there was a problem, like joint study by Bedford and Nakamura determined trace palladium responsible for reactivity, and biaryl coupling could not be reproduced with a range of iron catalysts. The iron catalyzed Suzuki biaryl coupling reaction appears to be for the moment at least out of reach. This was published in Tetrahedron Letters 2009, the comments, and coupling was observed with ppb levels of palladium, therefore palladium contamination is likely. So, Suzuki-Moira coupling may occur with this palladium contamination which is present in iron. So, now we will discuss cobalt based reagents in organic synthesis. So, electronic configuration is argon 3d7 4s2, and Nobel Prize was obtained by Alfred Werner in 1913 for his contribution to coordination chemistry, proposed correct structure of CONH363 plus. So, he proposed the structure and he got Nobel Prize in 1913. Oxidation state of cobalt most common +1, +2, +3. Cobalt 2 forms both tetrahedral and octahedral complexes, of course ligand dependent. Ligand is strong, then the geometry will change, and cobalt 3 prefers octahedral complexes. This one is blue, this is COCl2, and if you put in air then it becomes red. So, this is COCl2 6H2. So, this is very important in the color chemistry. Now, we will discuss many reactions like homocoupling reactions, CsP2 CsP2 cross coupling reactions, CsP2 CsP3 cross coupling, alkylation, CsP3 CsP3 cross coupling reactions, acylation we will discuss, cobalt catalyzed Heck type reactions we will discuss, Poisson-Khan reaction we will discuss, cycloaddition we will discuss, Nicholas reaction also we will discuss, and hydroformylation we will discuss. So, first we will discuss homocoupling reaction. First report on cobalt catalyzed cross coupling reaction describe the homocoupling reaction of Gigner reagents. In 1939, Gilman and Lichten-Walter obtained nearly quantitative yields of homocoupling product by treating aromatic Gigner reagents with stoichiometric amount of cobalt chloride. Here of course stoichiometric amount was used. In 1941, Kharas discovered that Gould yields of homocoupling products are obtained by using only catalytic amounts, that is 3 mole % of cobalt chloride, and stoichiometric amount of an oxidant such as aromatic or aliphatic halide. So, this is important contribution from Kharas. So, this is the Kharak reaction AR-MgBr, and this is the stoichiometric amount of aromatic halide COCl2 only 2.5 mole %, ether reflux 1 hour you get this AR cross coupled product. And the mechanism, chain mechanism was suggested. So, C6H5 reacts with cobalt chloride to generate this C6H5COCl plus MgBrCl, which is byproduct. Now, 2 C6H5COCl will generate this biphenyl and 2 COCl will form. Now, this COCl will react with C6H5Br, which is the additive here. So, this is additive, and you get this COCl Br plus the radical, phenyl radical is formed, and this phenyl radical can give biphenyl, benzene, biphenyl, then this trimer, tetramer plus other polymers is possible. This was published in JACS 1941. Now, we will discuss CsP2 cross coupling reaction, cobalt catalyzed coupling reaction between functionalized aryl halides and alkynyl acetates. So, this is aryl halide, this is alkynyl acetate or vinyl acetate, and with COBr to 5 mole %, manganese 10 equivalent, DMA pyridine solvent 15:2 to 50 degree centigrade, you get this cross coupled product. So, a CC bond is formed, this bond is formed in this reaction. So, what could be the mechanism? So, COBr2 with manganese. So, manganese is reductant, manganese itself is going to manganese 2 plus, and it is converting cobalt 2 to cobalt 1 or 0. So, cobalt 1 or 0 is forming, and now ARX will add. So, this is the oxidative addition, like earlier we have seen, this will form, and now this vinyl acetate will displace one X. So, X minus will eliminate and you get this. So, this carbonyl group coordinates with cobalt, and it can take geometry like this. So, carbonyl coordinates with cobalt, and cobalt also coordinates with iron, and now the 6 membered transition state is formed. Now, this aryl will coordinate with this. So, aryl, this CC bond will form here, like here, and you get this is the product. So, this is the newly generated bond, and this is formed down cobalt 2 or 3 acetate. Now, again manganese becomes manganese 2 plus, acetate liberates, and it becomes cobalt 3 becomes cobalt 1. So, oxidative addition and reductive elimination like this happens, and you get this cross coupled product. This was published in European JOC 2005. Some more CsP2 CsP2 cross coupling reactions, aryl cross coupling. Earlier we have seen aryl vinyl, now we will see aryl cross coupling, synthesis of unsymmetrical biaryl compounds by coupling of two aryl halides under cobalt catalysis. So, two aryl halides can be coupled to give biaryl compound. So, this is 2 equivalent XS, this is another functional group containing aryl halide with COBr2 20 mole percent, diphenyl phosphine 20 mole percent, manganese 4 equivalent, similar solvent DMF pyridine 6:1, 50 degree centigrade, you get this. So, the cross coupled product, here this bond is formed carbon carbon. So, what could be the mechanism here? Similarly, this manganese becoming manganese plus 2, cobalt 2 becoming cobalt 1 or 0. Now, this aryl X will do the oxidative addition, and so cobalt 1 becoming cobalt 3, and now this manganese will go to manganese X2, and this will form manganese will reduce this one, because here cobalt is 3, and this is cobalt 1. So, after the addition of a different molecule, AR dash X will oxidatively add here. So, you get this cobalt 1 again becomes cobalt 3, and now the reductive elimination will happen, reductive elimination. So, cobalt 3 becomes cobalt 1, and you get this cross coupled product. This was published in Anglo and the Chemistry International edition 2008. So, CsP2 CsP3 cross coupling also is possible. Alylation of aromatic organometallics, cobalt catalyzed coupling between aryl acetate and functionalized aryl bromides. So, this is the aryl bromide aryl acetate with cobalt bromide 20 mole percent, zinc 3.5 equivalent, zinc bromide 10 mole percent, PHBr 10 mole percent, catalytic acetic acid, acetonitrile, room temperature 3 hours, you get this allyl containing aryl group. So, here electron withdrawing group, so this is EWG group can be tolerated, this product is from 65%, and methoxy, this is EDG group electron donating, also the product is from a 60% yield. Now, if you use aryl acetate and functionalized aryl chloride. So, earlier we have seen aryl bromide, these are aryl chloride now. So, with aryl chloride, similar condition you can use cobalt bromide 40 mole percent, manganese 3.5 equivalent, instead of zinc now here manganese, and instead of zinc bromide here you have to use ferrous bromide 1 equivalent, catalytic acetic acid, MEC and pyridine 20:2, 50 degree centigrade 24 hours, you get this same product. Here also electron withdrawing groups is tolerated nicely 72%, 83%, and here also you get this is the ortho position, you get this product in 83% yield. So, most likely cobalt and zinc, cobalt bromide and zinc, you are getting this ZnBr, and after that ZnBr, this is reacting with aryl acetate, which is again of course activated by cobalt, and that is why this allyl product is forming. So, this was published in Organic Letters 2003. Now, we will discuss alkylation, benzylation of acetylene Gigner reagents, cobalt catalyzed benzylation of alkynyl magnesium halides. So, here alkynyl magnesium bromide is there, ArCH2X with cobalt acetyl acetone ACSC. So, acetyl acetone 2 mole percent, THF room temperature 4 to 12 hours, you get this product. So, this is the bond is formed carbon carbon, that is the benzylation. So, benzylation happens. And if you see the scope of this reaction, different benzyl groups containing compounds can be used like benzyl bromide, and here this alkyne, when R is equal to N-butyl you get 70% yield, R is equal to SiM3 you get 71. But if you use benzyl chloride, then for N-butyl case R is equal to N-butyl you get only 21% yield. So, yield is less here, yield less. However, if you use SiM3 yield is going to 82%. A ortho group can also be tolerated like methoxybromo. In this case very good yield, R is equal to SiM3 93%, here almost similar yield, N-butyl SiM3. So, the mechanism will be most likely with the Grignard, that we will see later, that cobalt 3 becomes cobalt 0 with this Grignard, and this cobalt 0 then coordinates with the alkyne magnesium as well as this ArCH2X, so that the cross coupling happens, and this was published in Tetrad Letters 2006. Some more on the alkynylation. Alkynylation is the cobalt catalyzed coupling between the alkynyl magnesium halides and alkynyl triplets. So, earlier we have seen aryl bromide, now alkynyl triplet was described by Hayashi in 2007. Here this alkynyl magnesium bromide and vinyl triplet is used. With same catalyst cobalt acetyl acetonate 3 mole percent THF room temperature you get this. So, this is enine. Enine compounds are very useful, you can get this way very easily. Suppose this one with octyl group containing, you get 88% with hexyl, and here the substitution is there, you can get this product in 98% yield. Also chemoselective possible cobalt catalyzed alkynylation of acetylenic Grignard reagents. So, here this is the vinyl triplet, this is the Grignard, that is what we are looking for the reaction, and you get this enine product. Now, if you put R3X, R3 can be also aryl also, so this product could be formed, that is what last reaction we have seen earlier, that this is when aryl, the aryl group is coming, and cobalt acetyl acetonate 3 mole percent THF room temperature 2 hours, you can get the selectivity. So, R3X when it is vinyl bromide you get 89:11. So, that means vinyl triplet is much more reactive than vinyl bromide. Now, if you use cyclohexyl bromide, of course, you get greater than 99:1. So, this is the forming, this is not forming, and this is 60%. Interestingly, if you have this one, paratolulyl iodide, here this product is formed selectively. So, what happens? This O triplet is much more reactive now this with iodotoluene. So, here also selectivity is very good, greater than 99:1, and you get this product 50% yield. So, this is very important. Chemoselectively, if you have a aryl iodide and vinyl triplet, the vinyl triplet will selectively couple to the alkynyl magnesium bromide. This was published in ChemCom 2007. Now, alkynylation mechanism we can discuss. So, as I told earlier, the cobalt 3 is first reduced to a cobalt 0 complex by 3 equivalents of alkynyl Grignard reagent 1. So, this is the Grignard reagent, this is cobalt acetyl acetonate. This is reducing to cobalt 0, which further accepts the attack of 2 equivalents of 1 to form bis alkynyl diet complex 5. So, again 2 equivalent attacks to the cobalt 0. So, the cobalt here they become 2 minus 8 complex. So, this is 8 complex is formed. Now, oxidative addition of alkynyl triplet 2 to 5 gives mono 8 cobalt to complex 6. So, this is alkynyl triplet. Now, it adds to here to the cobalt of course. So, this adds to the cobalt, and 1 mGbr will eliminate like this, mGbr OTF, and 1 mGbr will reside like this plus charge. Now this one, your both alkyne and vinyl group is present. So the reductive elimination will happen now. Which undergoes reductive elimination to give enine 3. So this is the product. And monoalkynyl 8 complex 7. So monoalkynyl 8 complex 7 will form. Finally, again it will react with alkynyl Gigner reagent with 1 to generate di 8 complex 5. So this is di 8 complex 5. This is the paper came from 2007. Now we will discuss CsP3 cross coupling. So benzylation we will discuss now. An example of cobalt catalyzed benzylation of an organo-zinc compound was first reported by Nochel in 1996. So this is the reaction benzyl bromide and this is the functionalized zinc iodide, cobalt Br2 10 mole percent, THF, NMP. So NMP is N-methyl pyrrolidone, that is also solvent, and minus 10 degree centigrade you get this. So this carbon and this carbon reacts and you get this product in 60% yield. This was published in Anglo on the Chemie International edition 1996. In 2004, Oshima achieved the coupling between secondary alkyl halides and benzyl Gigner reagents in the presence of COCl2 DPPP, diphenyl phosphinopropane. So this is the benzyl magnesium chloride. Now alkyl X with COCl2 10 mole percent. Here DPP is the ligand with THF 0 degree centigrade 2 hours you get this cross coupled product. And you can see the scope here. So Gigner reagent is benzyl magnesium chloride, secondary butyl bromide is the alkyl source and 70% yield you can get. With paramethoxy same you get 50% yield. Also with benzyl magnesium chloride and a secondary iodide also gives 62% yield, and cyclohexyl bromide or iodide gives good yield. Tertiary butyl iodide yield is less. And in this case 3 equivalent of Gigner reagent was used. So what could be the mechanism for this case? The reaction mechanism should involve oxidative addition of alkyl halide by a radical mechanism. The oxidative addition proceeds through a single electron transfer from an electron rich allyl or benzyl cobalt complex to the alkyl halide. So single electron transfer will take place from an electron rich allyl or benzyl cobalt complex, and this was published in Chemistry European Journal 2004. Now we discuss acylation, the cobalt mediated synthesis of aromatic ketones from aryl bromides and carboxylic acid anhydrides was reported by Pericon in 2004. So aryl bromide, this is anhydride with cobalt bromide 5 mole percent, zinc 1.5 equivalent, allyl chloride 15 mole percent, acetonitrile catalytic trifluoroacetic acid, room temperature you get this. So this is the acylation, and you can see the scope of this reaction: paramethoxy, paracyano, CO2 ET, F, CF3, methoxy, metamethoxy, metacyano, meta CF3 different group, and R defined anhydride. So this is anhydride with methyl, N-butyl, phenyl, methyl, N-butyl, phenyl, methyl, N-butyl, methyl. You get moderate to good yields. Some cases 10 mole percent has to be used COBr2, and some cases 7.5 mole percent COBr2 was used. This was published in Journal of Organic Chemistry 2004. Now we will discuss cobalt catalyzed Hake type reaction. The Hake reaction is a powerful tool for the elaboration of carbon-carbon bonds. However, the reaction still suffers some limitation. The use of alkyl halides having hydrogens atoms in the beta position to the halide atom leads to poor results, since the intermediate catalytic alkyl palladium species undergoes a very fast beta hydrogen elimination. So this is the problem in Hake reaction. If you want to use alkyl halide and if there is a beta hydrogen, that can be eliminated. But we will see with cobalt this problem can be solved. The cobalt catalyzed Heck type reaction is complementary to the classical paradigm catalyzed reaction, since it allows avoidance of this drawback. Like here Rx alkyl halide with olefin Me3SiCH2 MgCl 2.5 equivalent COCl2 DPPH. So, DPPH is this N dot NO2 pH. So, this is DPPH. With ether reflux 3 to 8 hours, you get this Heck coupled product, and this is the scope. This is of course NC12 H25I. pH AR is equal to pH, that is the styrene. You get this product in 57% yield. NC12 H25Br, you get 76%, here also 74%. Also secondary alkyl bromide can also be used, you get 73%. Cyclohexyl gives 84%, and tertiary butyl can also be used in this Heck coupling, and you can get 67% yield. So, this is very interesting. Defined primary, secondary and tertiary can be used in this Heck coupling. This was published in JAX 2002. So, what could be the mechanism for this Heck coupling reaction? So, COCl2 DPPH goes to cobalt 0, and after that Rx. So, this is the alkyl halide will react and generate Rx dot minus. So, there is a minus dot minus, and cobalt 0 become cobalt 1. Now, this Me3SiCH2 MgCl will coordinate with cobalt, so to generate this, and MgClX will be byproduct. Now, this Rx dot minus, after elimination of X minus, it generates R dot. So, this is radical. So, R dot radical is formed, and that will attack to the styrene. So, it attacks regioselectively at this carbon, so that this radical will be stabilized by phenyl group. So, that is the benzylic radical, and now this radical will react with cobalt 1 system to generate this. Cobalt become now cobalt 2, and after that elimination. So, this elimination will take place like this. You get this olefin, and this hydrido A is formed. So, this should be like this. So, HCO2, this ligand and DPPH. After Me3SiCH3, you get this active catalyst. So, this is the active catalyst cobalt 0. Now, we discuss Poisson-Khan reaction. This is very important reaction. Dicobalt octacarbonyl, the predominant cobalt carbonyl complex, has found wide applications in organic synthesis. It is prepared by the high pressure carbonylation of cobalt to salt. In solution, it exists in equilibrium between two forms, both of which obey to the 18 electron rule. So, this is dicobalt octacarbonyl, and this can stay like this. So, here all connected to cobalt, two carbon monoxide are in the bridged, and this is the Poisson-Khan reaction. Here an alkyne will be used, RL. So, this can be disubstituted RL. RL means this is the larger size, because you will see the regioselectivity is an issue. So, terminal alkyne gave better yield, size RL greater than RS. Now, an olefin strained cyclic greater than terminal, greater than disubstituted, greater than disubstituted, then electron poor alkene. So, electron poor alkenes are not very good substrate for this, and CO2 CO8 one equivalent, that is this solvent heat, you get this. So, what is this? This is cyclopentanone. So, you can see this is three components. This carbonyl group comes from carbon monoxide, this is the triple bond part and this is the olefin part. So, triple bond becomes double bond, olefin becomes carbon carbon and carbon monoxide inserts to give this carbonyl. Alkene regioselectivity hard to predict unless intramolecular. The reaction is completely regioselective with respect to the alkyne. The larger substituent always occupy the position adjacent to the carbonyl group in the product. However, the use of an unsymmetrical alkene usually leads to mixture of regioisomers. So, now we will see the mechanism. So, the reaction of dicobalt octacarbonyl involve insertion of carbon monoxide into the substrate resulting in carbonylation as the overall result. And similarly, the reaction of an alkyne with this complex result in the formation of stable organocobalt complex that exists at tetrahedral cluster 1. So, this is the reaction and tetrahedral cluster 1 is formed. So, this is very important. An alkyne reacts with dicobalt octacarbonyl to generate this. Here you can see that is the both pi bonds has been used to react with cobalt and with this is formed tetrahedral cluster. Tetrahedral cluster. This cluster can react with an alkene on heating to generate a cyclopentanone derivative via 2 plus 2 plus 1 cycloaddition. So, this is the detailed mechanism. Now, when olefin will comes after elimination of one carbon monoxide, the coordination will happen. So, intermediate 2 is formed. So, it is believed that the loss of carbon monoxide molecule from the tetrahedral complex followed by coordination with the alkene which insert itself in the CO-CO bond. So, now the insertion will happen. So, this is the insertion. This double bond inserts into cobalt carbon monoxide bond. This intermediate 3, now this is the intermediate 3 undergoes insertion reaction where carbon monoxide insertion takes place between the COA alkene bond forming the intermediate 4. So, this is the intermediate 4 is formed and which may undergo reductive elimination to give the product. So, here you can see this bond is broken and this alkene gets insert and now carbon monoxide gets insert into this bond. So, here carbon monoxide comes and this is the olefin part of course, this is the olefin part and now CO inserts here. So, you get this and after reductive elimination you get this 5-member ring is formed and here this R2 R1 stays like this. So, here R1 is bigger in size than R2. So, then you can get this selectivity R1 will be close to the carbonyl and after reductive elimination you get this cyclopentanone. So, this is R1, R2 and this is the olefin R. Now, we will discuss some intramolecular Poisson-Khan reactions. So, here the double bond and triple are in the same molecule with CO2, CO8, C7H16, 100 degree centigrade you get the two products. So, both are these are diastomers. Diastomers are formed and this intramolecular reaction defined additive has been used like amine additive here. This one the triple bond double bond is there with amine additive like ammonia. So, if you see the solvent co-solvent dioxane water you get only 0% yield. So, 91% starting material for this particular reaction. Now, if you react with 1 molar ammonia water you get 96% yield. So, base is effective. Sulfide additive can also be used like for this reaction if you see additive 3.5 equivalent dichloromethane 83 degree centigrade 30 minutes with additive like cyclohexylamine you get 15%. This is the amine additive that is not good, but if you use sulfide like N-butyl methyl sulfide you get 79% yield. So, amine and sulfide can increase the yield. Now, we will discuss cycloaddition reaction that is the Vollard cyclotrimerization reaction. So, dicarbonyl octacarbonyl that we have seen can be converted to eta 5 cyclopentadienyl dicarbonyl cobalt 0 which is the catalyst for Vollard cyclotrimerization reaction. This reaction is unique as it brings about 3 formation of a benzene ring in one step by 2 plus 2 plus 2 cycle addition of a dialkyne with a monoalkyne. So, this is the dialkyne and this is the dicobalt, this is the monomer dicobalt octacarbonyl 18 electron. Now, after 2 carbon monoxide elimination you get this coordination happens, and now this bond is formed. So, this you see 1 2 3 4. So, this bond is formed here. So, the cyclobutane ring is formed, and here also cyclopentadiene cobalt is connected with cyclopentadiene. This is 16 electron system. Again another alkyne will come. So, this is monoalkyne also again 18 electron it will get cobalt, and now the 4 plus 2 reaction will happen. Here a double bond will be there. So, after that you get this 4 plus 2, there is a bridged cobalt, and this bridged cobalt then eliminates like this, and again it coordinates with the pi system. So, here the aromatization happens actually. If you see, this is 6 membered aromatic compound, and with cobalt it is connected. Cobalt is 18 electron, and after that cobalt elimination 2 carbon monoxide and minus CpCO2, you get this product. So, this is very important. A dialkyne and a monoalkyne can give this bicyclic product in good yield. This was reviewed account of chemical research 1977. Now, we will discuss Nicholas reaction. So, Nicholas reaction is an organic reaction where a dicobalt octacarbonyl stabilized propargylic cation is reacted with a nucleophile. Oxidative demetallation gives the desired alkylated alkyne. It is named after Kenneth M. Nicholas. So, this is the substrate here. If you see, this is propargylic system, and of course, this is a quaternary center, and with CO2 CO8 Lewis acid nucleophile oxidation last step, then you get this OR4 group is replaced by a nucleophile. What could be the mechanism? So, as we have seen, the alkyne will coordinate with this. So, alkyne protection happens, and now with Lewis acid or strong acid like HbF4, you can generate this carbocation, because this carbocation is tertiary carbocation. So, it is stable. Also, it can isomerize like this. See this isomerization, that is the resonance form is here, and then a nucleophile will attack here to get this. So, nucleophile will attack to the carbocation, and after oxidation you can remove this cobalt system. So, this is cobalt here acts as a protecting group, and you can functionalize a propargylic system. Nucleophile can be electron rich ARH, ketone, allyl Si, R3, etc. And this was published in Journal of Organometallic Chemistry 1972. Last reaction we will discuss hydroformylation. So, one of the most industrially important reaction using cobalt is definitely the hydroformylation. This reaction is catalyzed by dicobalt octacarbonyl. This reaction inserts a carbonyl group in an alkene, thereby giving rise to aldehydes. It is also known as the oxo process. So, this is the reaction. So, high hydrogen pressure, of course, you have to maintain high hydrogen pressure. This is propene, 2 carbon monoxide H2O gives this propanol, and also this. This is the Markovnikov product, Markovnikov. This is anti-Markovnikov product. This is N and this is iso. So, both the linear isomer usually referred to as N product and the branch isomer iso product are produced. The use of bulky ligands like tributyl phosphine diminishes the extent of branch aldehyde formation, improves the N iso ratio. So, this is the mechanism. So, at a very high pressure like 100 bar, dicobalt octacarbonyl reacts with hydrogen gas to form tetracarbonyl hydridrocobalt. So, this is the tetracarbonyl hydridrocobalt is formed. This is the active catalyst. So, HCOCO4 after carbon monoxide elimination you get this, and then the alkene. So, here propene coordinates with the cobalt and you get this. So, what happens here? The H also reacts and CO also reacts. So, if CO reacts here and hydrogen reacts here, that is the Marconi curve. So, this is the Marconi curve, and this is anti-Marconi curve. Again one carbon monoxide comes, so the cobalt coordinates with 4 carbon monoxide and this formed, and now the insertion will happen. So, insertion. So, one carbon monoxide inserts into this C cobalt bond. So, you see this carbonyl group inserts and H2O comes, it generates this one H hydrido tricarbonyl cobalt and you get this products. So, these two products are formed. So, in today's lecture, first we have discussed iron based reagents. So, in iron based reagent we have discussed Coleman's reagent, also we have seen the sodium hydroxide treatment and then the functionalization. Binary carbonyl iron complexes we have seen, alkene iron complexes we have seen, then we have discussed cyclopentadiene iron carbonyl, this we have seen. Fiddle-Curves alkylation we have discussed because ferric chloride is a good Lewis acid. Then we have seen the epoxidation reaction, then we have discussed Kharas reaction we have seen, aminochlorination reaction we have seen, and we have seen also different coupling reaction like Kumada coupling, Negishi coupling. This reaction can be performed also with iron. And then we have discussed cobalt chemistry. In the cobalt chemistry we have first discussed homocoupling reactions, we have discussed CsP2 sp2 cross coupling reaction, sp2 sp3 cross coupling reaction, alkyne annihilation reaction, CsP2 CsP3 cross coupling reaction. We have seen different alkyl halide like primary, secondary, tertiary can be used. Then we have seen the acylation, then we have seen the cobalt catalyzed Heck type reaction, then we have seen the Poisson-Khan reaction. This is very important reaction, a alkyne, a alkene and cobalt carbonyl ultimately will give cyclopentanone compound. So, this is very useful reaction. Then we have seen the Nicholas reaction we have seen, and cycloaddition reaction also we have seen, and lastly we have seen hydroformylation and aldehyde, that is the linear aldehyde, also branch aldehyde can be obtained, and if you use tributyl phosphine then the normal isomer can be increased. Thank you.